Hi everyone, this is Aishwarya and I will be discussing Vigenere Cipher in this video. Talking about the history of Vigenere Cipher, it was first discovered in 1553. The basis of this cipher seems very simple at first. Here we basically map alphabets to other alphabets. But despite its simplicity, this method was unbreakable for about 300 years before someone could decode it. That's why it's also called the indecipherable cipher. Talking about how this method works, so it basically encrypts plain alphabetical text using a secret key and generates an encrypted alphabetical message. This secret key is also made of alphabets. One can imagine this to be a interwoven series of multiple Caesar ciphers. Also, this method employs a form of polyalphabetic substitution, which means that a single alphabet can be mapped to different letters depending upon its position in the plain text. Talking about mathematical representation of this method, let's start with encryption. Now, in encryption, we need to code a message in plain text. How can this be calculated? So, here it can be represented with this simple mathematical equation. This can be calculated by adding the numerical equivalent of our plain text with the secret key, and then we take a modulus of 26. This is how we get the coded message. Now, how can we represent decryption in mathematically? Pause the video for about 10 seconds and try to think about this. Yes, it's quite simple. Here we need to find the plain text from the coded message. Thus, what we do is we subtract the numerical equivalent of the secret key and then we take a modulus by 26. Here P is the plain text, K is a secret key, and C is the coded message. Why do we use a modulus of 26? Because we have 26 alphabets. Now let's dive into some examples. Example 1. Here we want to encrypt the message Aish. And for this video, let's take our secret key to be mango. Also because I love mangoes. Now we write our message on the top row and then we write our secret key below it, matching the positions in a sequence. Why are we doing this in a gridded manner? Just for the simplicity of showing the calculations. So here we write the corresponding numerical value of each letter from this table on the right side here. So A corresponds to 1, I corresponds to 9, S corresponds to 19, and H corresponds to 8. That's why we have here 1, 9, 19, and 8. Now, similarly, let's write the numerical equivalent values of mango, which is our secret key. M stands for 13 here. A can be written as 1, N can be written as 14, G can be written as 7, and O here can be written as 15. But we don't really need this letter because we don't have any message to encrypt. So moving forward, we are going to keep this value as blank. Try to remember the mathematical representation of encryption. Here, first we add the values, numerical values, and then we take a modulus of by 26. Listing down the steps that we are going to do here. First, we add these values. So 13 plus 1 is 14. 9 plus 1 is 10. 19 plus 14 is 33. 8 plus 7 is 15. Now the next step is to take a modulus of 26. So what we have here 14 mod 26 is 14 because we can have quotient as 0 and the remainder as 14. So 26 into 0 plus 14 gives us 14. Similarly, 10 mod 26 is 10. Now what will be 33 mod 26? What will be the quotient and the remainder here? So we can have quotient as 1 and the remainder as 7. So 26 into 1 plus 7 gives us 33. And 15 mod 26 gives us 15. So now we have calculated the modulus and all calculations are done. Now we just need to map these numerical values with the corresponding alphabets from this table on the right side. So 14 we have N, 10 we have J, from 7 we have G, and from 15 we have O. So it should be NJGO. This is our encrypted message. Not very intuitive, right? Yeah, so this serves the purpose for our encryption. Now let's see an example to decrypt a message, that is to decode a message. So here, let's decrypt the encoded message in our previous slide. We have NJGO. So again, similarly, we'll list down the letters and we'll list our secret key corresponding to its positions. Next, we write down the numerical equivalent values of these letters over here. Now remember what was the process, what was the mathematical equation for decryption? First, we take subtraction of the coded message by the secret key, and then we take a modulus 26 of those subtracted values. So here listing down the steps that we are going to do. First, let's do subtraction. So 14 minus 13, we have 1. 10 minus 1, we have 9. Now 7 minus 14, we have minus 7. And 15 minus 7, we get 8. Now let's take a modulus 26 of these values. So for 1 and 9, the values are pretty straightforward, right? 1 more 26 will be 1 and 9 more 26 will be 9. Now what will be the modulus of minus 7? Here it will be 19. How did we come up with 19? So we first try to find the closest number to minus 7, which is a multiple of 26. So essentially we first need to find a quotient and then a remainder. The remainder will be our modulus solution. And remember that the remainder should be positive. So here will our quotient be 0? So when I do 26 into 0, I still get a negative remainder. So no. So will the quotient be minus 1? Yes. 26 minus 1 will give us minus 26 plus 19 gives us minus 7. And the remainder here is 19. Thus, 19 is the solution for minus 7 mod 26. So that is how we get 19 here. And 8 mod 26 will be 8. Now mapping back the alphabets for these numerical values, from 1 we get A, from 9 we get I, from 19 we get S, and from 8 we get H. And this is our plain text which we initially encoded, which was Aish. Now let's look at another example which will be a bit longer than the messages that we have seen. So let's try to encrypt love dogs, and I just write down love dogs. But here, in order to encrypt this message, we do not need any spaces for the simplicity of calculations. So let's just remove the space. So I have just written love dogs, and I just write down my secret key corresponding to the position. So here you can see that I have written mango, and here the secret key finishes. So how do I cover the remaining letters? So essentially, you stream the same secret key along the length of your plain text. So here we just need additional 3 letters, which is MAN. What if your message is super long? It's like 100 characters. Then here you will have mango This is like 5 times, so 100 divided by 5 is 20. So we'll have mango stream 20 times, like mango, 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 and so on. So now we have our plain text, and we also have the secret key corresponding to its position. Now let's do the calculation. Remember that for encryption, we first need to add the values and then take a modulus 26. So here I have brought the numerical equivalent values of all these letters here, and then let's do our calculations. First we do additions. So we have 12 plus 13 as 25, 15 plus 1 as 16, 22 plus 14 as 36, and so on for the rest of the values. Now let's take modulus 26. Now we know that 25 and 16 are pretty straightforward, so we just write them as it is. Now 36 mod 26. How do we calculate it? So here the quotient should be 1 and the remainder should be a positive value. So 26 into 1 is 26 and 36 minus 26 gives us a 10. So 36 more 26 is 10. For 12 more 26 is 12, 19 more 26 is 19, and again we have a higher number than 26. Here the quotient can be 1 and the remainder can be 2. So we have 28 more 26 as 2, 8 more 26 as 8, and 33 more 26 as 7. The quotient is 1 and the remainder is 7 in this case. Now we have calculated our encrypted values and we just need to map it to the corresponding letters. So from 25 we have Y, from 16 we have P here, from 10 we have J, from 12 we have L, from 19 we have S, from 2 we have B, from 8 we get H, and from 7 we get J. This is our encrypted message. It's very super non-intuitive, right? Yes, so this definitely serves our purpose. Now let's look at our last example where we decrypt a message. So let's take the same encoded message and let's try to decrypt it. So here we have written down our coded message and below is our secret key streamed up to the length of our coded message. Next, we write down the numerical equivalent values of our coded message here and of our secret key below it. Now, what were the process of decrypting a coded message? First, we do subtraction and then we take a modulus 26 of those values. Let's think down the steps here. Let's do a subtraction. So we have 25 minus 13 as 12, 16 minus 1 as 15, 10 minus 14 as minus 4, and so on. Now next, we need to find the modulus 26 of these subtracted values. So 12 and 15 are pretty straightforward because in both the cases the quotient is 0. So 12 mod 26 is 12, 15 mod 26 is 15. Now what is minus 4 mod 26? It's 22. How did we come up with this value? So we first try to find the closest number to minus 4, which is a multiple of 26. Now will the quotient here be 0? No, because we get a negative remainder. We remember that in order to find the solution, we need a positive remainder. Now will the quotient be minus 1? Yes, because 26 minus 1 gives us minus 26 and plus 22 gives us minus 4. So here the remainder is 22 and it is a positive integer and thus the solution for minus 4 mod 26 is 22. Now how do we get 5 and 4 mod 26? It will be the same values because in both the cases the quotient is 0. Now let's find minus 11 mod 26. So here again the quotient will be minus 1. So 26 into minus 1 will give us minus 26. Minus 26 plus 15 gives us minus 11. So here the remainder is 15 and which is also the solution. Now 7 mod 26 gives us 7. and minus 7 more 26 as we calculated in example number 2 gives us 19. So finally we have our decrypted message, and now we just need to map it to its corresponding alphabets. So from 12 I get L, from 15 I get O, from 22 I get V, from 5 I get E, from 4 we get D, from 15 again we get O, from 7 we get G, and from 19 we get S. And we have our plain text message, which was love dogs. Let's talk a bit about the limitations of this method. So compared to today's standards, it is now easily broken. And one of the methods that is used to break it is the frequency analysis. So here we know that the secret key repeats along the length of the message. And the second thing that we can assume is that some of the letters are more used frequently in the English language. For example, the letter A is used more frequently. So, keeping in mind some of these pointers, frequency analysis can be done, which can be used to break this encrypted message. This brings us to the end of our video. Thank you for watching.